and let's maximize and have here. Thanks everybody for being here, and this is our third presentation today. We have done one in English, one in Spanish, and actually this is tier one, so I can consider that the first two were kind of rehearsals, and I hope to do this one even better. We have I'm still going familiar with this method of doing webinars, and I am new with webinars, so I apologize in advance. Any question you have during the presentation, you can answer in the section chat that is in the left side under the picture, or you can do a question that is in the section questions and answers. Questions and answers is not being viewed by anybody except by the host, that is Gavin, Jason, Juan Carlos, or me. And chat is viewed by everybody. Questions and answers is under the area where we will show the Acrobat or the PowerPoints. Okay, so the first thing I want to do is to show you the outline of what we will cover, and the plan is that this is the first section of 3 different sections that will focus in to improve everybody's skill in the speaker system align. The first part will discuss about single filters, basically high pass, low pass. You can think that today is the more basic information. The second session that will be done in July, in one of the first weeks of July, it will take high pass and low pass and combine filters to learn what's going on when we play high pass and low pass together. And the third section will take high pass, low pass, and add 2 speakers. So in the third section actually is the ultimate goal of this, to do all the process of the alignment. Let me explain in detail every one of these sections. The plan for today that is in the next 40-45 minutes, we'll discuss about high pass or low pass as single filters. We will discuss about some of the parameters, that is like the cutoff frequency and the order and the topology of filters, as you can see here, Butterworth, Linkwitz-Riley, and Bessel, that are the most familiar for everybody. We will discuss some filters that actually in some way makes that people ask so many questions, and this complex filters slope, that is Chebyshev or Elliptic. Then, after explaining this, we will cover what I personally think that is the most important topic with filters, that is group delay. The group delay is this: every time we use a high pass or low pass, the filter adds delay to the electric signal. But it's not a constant delay. As we will see in a few moments, high frequencies delay will be very small, but low frequencies delay will be very big. And since some frequencies is having delay but not other frequencies, this is called group delay. Then we will view the delay as in the common analyzer that you may be using in these days, and we will use a phase display to understand the group delay of filters. And then we will use another way to view the information using what is called the impulse response. So we will view the group delay according to impulse response, that is a common measure method in analyzers. The second section that will be in July, it is taking high pass and low pass, the ones that we explained today, and combine them electrically without taking into account still any speaker. So we will learn about what is a crossover point. We will see that the crossover point, that is the intersection between a high pass and low pass, changes not only when we change the cutoff frequency or the frequency of the filter, but also doing level or what is called gain adjustments. We will see a lot of combinations from 6 dB to 48 dB in Butterworth or Bessel, and from 12 dB to 48 dB in Linkwitz-Riley. And we will see what is the consequence of changing the combination of slopes as phase and as group delay from 6 dB to 48 dB, and see the implications as when we change the slope, sometimes the crossover point can have summation, sometimes the crossover point can have a cancel. And we will learn a little bit how to align or how to equal the crossover point in time to produce summation, and we will do this in two-way system, three-way system, and four-way system. And in the month of August, that will be the last part, session 3, we will understand the transducers before attaching the filters to the transducer. So we will take woofers and compression drivers and show graphics of frequency response, phase response, group delay, and the input response. We will learn about sensitivity in the transducer and the voltage gain in the amplifiers. And then we will study what is the overlap range in transducers. And according to the overlap range, we will investigate what is the most appropriate crossover point, because we will investigate the polar pattern. The polar pattern will make us construct a special study that is called the beam width, and we will compare the beam width doing measurements with an analyzer on axis and off axis. This information about the directivity will help us to fix what is the appropriate crossover point. And as soon as we have the crossover point, we can go to the process of the speaker alignment. We will align or adjust the level and the phase or time. We will do the phase alignment using the changes in the slope or order of the filter. We will use electronic delay, or we will use electronic component that is called all pass for doing the phase alignment. We will compare doing the phase alignment using what is called the philosophy of same slope at the crossover point, or using different slope at the crossover point to see the consequences. And then we will also study what happens if we change what is the crossover point, because we will compare measurements on axis and off axis. This will make us realize the importance of matching the beam width for selecting the crossover point. And the last part of the last presentation will be what happens to the phase alignment as soon as we play with changes in gains in different bands in the controller. So let me bring here the presentation right now. I will come here, share document, and this is from my content, filters part 1. Okay, and this is coming here, bring here, and bring it big. Okay, we will start providing some terms, the terms that we will use for this explanation. After explaining the terms, we will explain the different slopes of filters, then the topology of single filters, that is Butterworth, Linkwitz-Riley, and Bessel, and after that we will go to complex filters that are the Chebyshev and Elliptic. In that part we will do a pause before going to the group delay, just to be sure that you don't have any question. Okay, so for practical reasons, I decide to classify the behavior of the filters with these names: single slope, and single slope when the filter is having a roll-off that is a continuous roll-off. And I decide to have the term complex slope when the roll-off it's very strange, like what you see. You see roll-off, then some recovery and a second roll-off, or some roll-off and then recovery and then just gain reduction. Or you can see that in simple filters, single slope, the area that is not being filtered maintains flat here, but in complex slope you can see that area that's supposed to not be filtered is showing some variations in this area. So the filters that we can classify as single slope are using the names Butterworth, Bessel, standard or normalized, and Linkwitz-Riley. This will be explained in a few minutes. And the filters that are using complex slope is Chebyshev 1, 2, or Elliptic. So let's define the labels that we will use for this presentation. I decide to use the labels that are commonly in books or in a lot of documentation. So the area that is not being filtered, that you try to maintain untouched, is called the passband, and the area that you plan to be filtered is the stopband. In a low pass filter, the passband is the low pass. But in a high pass filter, the passband is the high pass. So high pass filter, passband is the high. Low pass filter, passband is the low. In the low pass filter, the stop band is called the high cut, and in the high pass filter, the stop band is called the low cut. Apart from this, we have what is called the cutoff frequency. Normally people say it's the crossover point, but I prefer to not say crossover point unless we have two filters that will be combined. When I don't combine filter, I prefer to call cutoff frequency. Then you can see here that that in the crossover point we can see some sort of drop. So this means that cutoff frequency is not exactly where the level still is zero. Cutoff frequency, we have some level of reduction. And you can see that exactly in what I show as cutoff frequency, we have already some attenuation. In this case, it's 3 decibel of attenuation. And then we have the slope, that is the ratio of the attenuation. Sometimes this can be called slope. When it's called slope, it's referred as decibel per octave, and sometimes it's called as order. Order is just simple a number like 1, 2, 3, 4, 5, etc., etc. So in the high pass, you can see also cutoff frequency and the slope. Let's focus in the different slopes. Slopes as referred as decibel per octave, and they go in multiples of 6 dB steps. So this means that the smallest slope typically is 6 decibel per octave, and it goes in multiple like 6 decibel, 12 decibel, 18 decibel, 24 decibels, and goes on. And if you refer as order, every order is the slope divided over 6. So this means 6 decibel per octave over 6 is first order. 12 decibel per octave divided over 6 is second order. 18 decibel per octave divided over 6 is third order. 24 decibel per octave divided over 6 is fourth order. And pay attention here, because I am showing right now the cutoff frequency here to be exactly at 1K. So this is where we have to start to count the roll-off. If 1K is the cutoff frequency, 1 octave before this, it's 500 Hertz, and this is -6. 2 octaves before this is 250 Hertz, and this is -12. 3 octaves before this is 125 Hertz, and it's 18. 4 octaves before this is 63 Hertz, and this is 24 dB. So the roll-off is 6 dB per octave. Something that can produce more dramatic attenuation, it's second order. This is second order, and you can see for the very first octave we have 12 decibel of attenuation. In the previous example, for the very first octave it's just 6 decibels. So we can say that the second order filter is twice more powerful than the first order. And you can see that in only 2 octaves it drops 24 dB. In the first order filter, we need to spend 4 octaves in order to drop 24 dB. The next filter that we will see is third order, 18 decibel per octave. In the very first octave, it drops 18 dB. And the second octave, 36. And goes on. The next filter in terms of capacity or power is fourth order. You can see that fourth order, it is 24 decibel per octave. So for the very first octave, it's dropped 24. So this one is twice more powerful than second order. Second order needs 2 octaves for going 24, or is 4 times more powerful than first order. First order needs 1, 2, 3, 4 octaves to do 24 dB. Several processors, especially in the old days, in the days of analog processors, used to be 24 dB filters, like the graphic that I am showing here. In these days of digital, it's very common to see a lot of controllers that can have more than 24 dB. So let me show you. This one is 30 decibel per octave. The next one is 36 decibel per octave. The next one is 42 decibel per octave. The next one is 48 decibel per octave. From the controller that I am using, the maximum capacity based on what the designer did is 48 decibel per octave. But it's possible to find controllers that can do more than 48 dB. I had the opportunity to measure some controllers that can do 96 decibel per octave. So this means order number 16. This means that in a processor that can do 96 decibel per octave, you can have in the very first octave in 500 Hz 96 dB roll off. And the other important thing here that you have to understand, then order number 8 in only one octave can do what in 2 octaves you need with order number 4, or what you need with order number 2 in 4 octaves. We can think that the higher the order is better, because the higher the order we can produce more isolation between the bands. I can see a question from Jorge. Jorge said according to the presentation in Spanish. Let me answer. Jorge, la presentación en español fue hace 2 horas. Te sugiero entrar a la página de Meyer Sound a fines de junio para que puedas entrar otra vez a la presentación en español. Se repetirá en las primeras semanas de julio. Well, let's continue. And what is the difference between Butterworth, Linkwitz-Riley, or Bessel? Okay, Butterworth is what is considered to be the oldest filter being described. It was described in a paper from 1930 written by a British engineer, Stephen Butterworth. The document name is On Theory of Filter Amplifiers. And you can see that what is the main feature of Butterworth? It is that any option of Butterworth regarding the roll-off or slope always cut at -3. You can see here all the options, second order, fourth order, sixth order, eighth order, the one that I have here, always cut at -3. Because of this, you can see that before the crossover point, a little bit before, you can see that this is a little bit differences in the graphics. You can see the one with less order produce in this area more attenuation, and the one with more order produce in this area less attenuation. So you can see second order attenuate 1 octave later, 12 dB, fourth order attenuate 1 octave later, 24 dB, third order attenuate 1 octave later, 36 dB, eighth order attenuate 1 octave later, 48 dB. But all of these cut at -3. Then the next option historically is called Bessel. Bessel is a filter that was described by an engineer in 1949. The name is W.E. Thomson. It's very strange because the filter may be called Thomson, but Thomson explained in the document Delay Network Having Maximally Flat Frequency Characteristics that his idea about constructing this filter is being according the use of Bessel polynomials. So even when Bessel has not the idea to construct the filter, the people call this filter Bessel because Thomson explained about Bessel polynomials. What is interesting in this Bessel approach is that the area before the crossover point in any order is exactly the same, and Bessel cut at -3. Let me go back to the previous one, and you can see that the area before the crossover point changes, but in Bessel the area before the crossover point is identical. And in the Butterworth, all the crossover points or all the cutoff frequency, it is -3, and the Bessel, all the cutoff frequency also is -3. But Bessel is having something very, very particular, and is this. If I go 1 octave beyond the cutoff frequency, the second order filter is not 12 dB, it's around 9. The fourth order filter is not 24 dB, it's around -15. The eighth order filter is not 48 dB, but it is around -16 decibels. So as you can see, Bessel is not matching the attenuation that we expect after the crossover point. The next filter, historically, is being described in 1978 in a conference for the AES, and the name of this conference is called Networks for Non-Coincident Drivers. This paper was written by Siegfried Linkwitz and Riley, two engineers of the computer company Hewlett-Packard. And the idea of the Linkwitz-Riley is this. All Linkwitz-Riley caught at -6. And as we will see in the next presentation in July, having -6 dB offers very nice advantage, because if you have a high pass and a low pass and cross them at -6 and you do phase align, the combination of these two filters will go flat. So this is the filter that theoretically can produce the more flat response without using EQ. And you can see that the Linkwitz-Riley is producing the attenuation that we expect according to what we are looking for 1 octave later, or 2 octave later, or 3 octave later. Then, if you remember, in the situation of Bessel, the area after the crossover point is not matching. So, in 1998, I guess, an engineer from the American company Rain came with this idea. What happens if we intentionally shift the cutoff frequency in order to produce that the attenuation match exactly where we expect, in a way that in a low pass filter we shift down the frequency, but in a high pass frequency we shift up the frequency? Let me show. So this is the Bessel, and the idea from 1998 from Ray Miller is what is called normalized vessel or rectified vessel. So the idea of Ray Miller is why we don't bring down the filters in a low pass or bring up the filters in order to match the decibels per octave, 1 octave after the cutoff frequency. After doing this, he redefined what is the cutoff frequency, and then you can see that it's not anymore -3. You can see that in the second order, the cutoff frequency right now is -4.5. In the fourth order is -7.5. In the sixth order is -10.5. And in the eighth order is -13.5. So this is what happens when you have a vessel with normalization. So vessel with normalization, or vessel with a standard vessel with non-normalization, is exactly the same vessel. It's just the philosophy of defined cutoff frequency. In vessel standard, the cutoff frequency is defined at -3. And in vessel with normalization, the cutoff frequency will have different level according to the different order. Having explained about the single filters, single slope, let's go to complex slope filters. In the situation of complex slope filters, we have two options. One is called Chebyshev. Chebyshev is a mathematician and an economist from Russia. His name is Pafnury Chebyshev. I have been told that in Russian it's pronounced something like Chebyshev. Well, in this filter, we have not only the parameter cutoff frequency, and we have not only the parameter of the order, but we have also a third parameter. The third parameter is called passband ripple. And the passband ripple is a value that is expressed as decibels. In this one, I am using a passband ripple of 3 decibels. And I am showing here an orange rectangle that shows the variation in the passband. The variation goes from 0 to around -3 here. And this variation is known as ripple. Later I will show you what happens if I change the ripple, or if I change the order. So Chebyshev type 1 produces ripple in the passband, while Chebyshev type 2 produces the ripple in the stop band. In this case, the stop band shows the roll-off, then recover, and then a second roll-off. And the level of the recover is the level of the ripple parameter. In this case, the parameter of the ripple says 3 dB. So that is the reason that this recovery is 3 dB lower than the 0 dB. So this is Chebyshev type 2. Let me go back. Chebyshev type 1 is a Chebyshev that produces ripple in the passband. Chebyshev type 2 is a Chebyshev that produces ripple in the stopband. And then we have elliptic. Elliptic is a filter that was described around 1950 something, maybe 1958, before 1960, by a German engineer. The name is Wilhelm Cauer. And some people call to the elliptic filter called Cauer filter. And what is the difference between elliptic and Chebyshev type 1 or 2? Well, the difference is that the elliptic filter produces ripple in the passband and also produce ripple in the stopband. So you can think that elliptic filter it's a Chebyshev type 1 plus Chebyshev type 2 simultaneously. But nobody calls this Chebyshev type 1 and 2. People call elliptic. And it's better that you understand this. Never call to elliptic a Chebyshev type 1 or 2. It's elliptic. But maybe you can differentiate, realizing that elliptic will have ripple in the passband and in the stopband. So let's go more in detail with the filter Chebyshev type 1. In the Chebyshev type 1, I am having here 4 measurements, where the 4 measurements are exactly the same order, are exactly the same cutoff frequency. But what I am changing is the parameter ripple. So you can see that around 700 Hertz, I have 3 dB ripple, or 6 dB ripple, or 9 dB ripple. So something that is important to clarify is that you cannot customize at what frequency you want to set the ripple. The ripple goes in this frequency. If you want to make the ripple change frequency, you have to change the cutoff frequency. And let me show you what happens when we show Chebyshev type 2 changing the stopband ripple. So in this case, you can see that the ripple shows the value of 3 dB or 6 dB or 9 dB. Very interesting, because as soon as we change the value of the ripple in Chebyshev type 2, the area close to the cutoff frequency changes the roll-off, similar to what we saw with Butterworth filters. So you can see more dramatic roll-off or less dramatic roll-off closing to the crossover point. Then let's go more in detail with the Chebyshev type 1. Here what we have is 4 different slopes of Chebyshev. This one is first order, third order, fifth order, and seventh order. What they have in common is that they are odd orders. And the feature of odd orders in Chebyshev type 1 is that they produce attenuation in the ripple. You can see here it drops down, down, and down. And also, as you can see, the higher the order, the more ripples. Lower order, less ripples. Higher order, more ripples. What is pretty confused several times is that if I show even orders produce positive ripple. Even orders, you can see that the ripple goes higher than 0. And it's very important to keep in mind that you don't have the possibility to decide that I want to have positive ripple or negative ripple in even orders. Even orders are always positive, or orders are always negative. So the parameter is not positive or is not negative. The parameter is just decibels. As soon as you change the order, the filter will go up or down in the ripple. The other thing to explain is this. If I am having third order, I have 1 ripple area. If I have in a second order or fifth order, I have 2 ripples. Seventh order, I can see 3 ripples. If I go to second order, I can see 1 ripple. Fourth order, 2 ripples. Sixth order, 3 ripples, and eighth order, 4 ripples. Let me show you a small trick that I have been using for several years, in a way that when I saw with an analyzer a graphic, I immediately can recognize if the filter it is if the filter is, let's say, a second order or third or fourth when we have Chebyshev type 1. Look at this. The trick is this. I locate the flat area. This is flat area. And after the flat area, I check how many times the direction of the graphic changes. So right now the graphic goes down. This is one change. Goes up. This is second change. Goes down. This is third change. 3 changes is third order. Let's see if this works with fifth order. This is flat. Go down one time. Up second time. Down third time. Up fourth time. Down fifth time. This is fifth order. Seventh order will show 7 changes. So this is flat. Go down 1, 2, 3, 4, 5, 6, 7. The same apply for even orders. So in even orders you can see this is flat and then go up. This is one change. Goes down. This is the second change. This is second order. This must have 4 changes. Let's see. Flat 1, 2, 3, 4. Brilliant. This is sixth order. Flat 1, 2, 3, 4, 5, 6. This is 8th order. Let's see. Flat 1, 2, 3, 4, 5, 6, 7, 8. 8 orders. And one more thing that I have to clarify. Chebyshev type 1, order number 1. If the ripple is 3 decibels, it's exactly identical to Butterworth. So if you use an analyzer and you want to compare amplitude, phase, group delay, impulse response with a Butterworth first order that is adjusted at the same frequency cutoff of Chebyshev type 1, order 1, with the ripple of 3 decibels, the filter will show exactly the same graphic. And by the way, I just remember that I forgot to mention that Bessel rectified or unrectified order number 1 is exactly the same as Butterworth order number 1. So Butterworth order number 1 measured with an analyzer is the same as Bessel order 1 and when it's not normalized. But Bessel order 1 normalized is the same as unnormalized because the Bessel order 1 don't require normalization. Let's go to the Chebyshev type 2. The Chebyshev type 2, if you remember, produced the ripple in the stop band. So I have here the stop band, and you can see the Bessel order 1 shows 1 attenuation. The Bessel order 3 shows 1, 2. Sorry, I say Bessel. I apologize. I must say Chebyshev type 2. Let's go back. Chebyshev type 2 order 1, 1 roll off. Chebyshev type 2 order 3, 1, 2, 3. 3 changes in direction. Chebyshev type 2 order number 5. Let's go flat. 1, 2, 3, 4, 5 changes in direction. Chebyshev type 2 order 7 goes flat. And then 1, 2, 3, 4, 5, 6, 7 changes in direction. Then let's see Chebyshev even orders. Something important is that even orders, they end in the edge flat, 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 flat. But odd orders in Chebyshev type 2, they end with roll off, roll off, roll off, roll off in the edge. So this means that if you are using a low pass, the upper edge will be attenuation. If you are using a high pass, the lower edge will be attenuation with odd order Chebyshev type 2. But with Chebyshev type 2, low pass, the upper edge is flat. And if we are having a high pass, the lower edge is the one that will be flat. But anyway, we can count how many changes of direction from flat. This is flat, 1, 2, 2 changes in direction. This is order number 2. Order number 4 is 4 changes in direction. 1, 2, 3, 4. Order number 6, 6 changes in direction. 1, 2, 3, 4, 5, 6. And order number 8, 8 orders in direction. 1, 2, 3, 4, 5, 6, 7, 8. At this point, the explanation about slopes and topology of filters, Butterworth, Linkwitz-Riley, Bessel, and Chebyshev and Elliptic, is being finished. Before I advance to show group delay, I want to ask you people if you have any questions regarding these topics before entering in group delay. By the way, group delay is the most important topic. So let me read if in the chat window we have questions. No. Questions and answers. I don't have any question. Okay, let me advance. Yeah, okay. Before advance, I can remember that. Let me stop sharing for a moment. And let me see if I need to share something else. I will show you this filter. This is a filter that is a low-pass filter. This low-pass filter, it is from one processor, and if you are familiar with Meyer sound controller Galileo, it's a digital speaker controller. This is the graphic of Galileo low pass. And what we can learn here, that Meyer sound Galileo is showing in the stop band 1 change, 2 change, 3 change. So what we can learn is that Galileo is using Chebyshev type 2 order number 3. And if I have 0 exactly here and I have 3 decibels per division, then from the current 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30. It's around 28 decibels of ripple. So right now you can see a commercial processor that is using a filter as the one that I have described. But also, if we pay attention to the area before the cutoff frequency, this area shows a little bit of increase. And this little bit of increase goes up and down of around half of a dB. So this means that this area is rippling the pass band. For this reason, as we can see here, this is an elliptic filter. Let me close this. And this filter is not only part of the Meyer sound controller Galileo, that is digital, but in the days of analog controllers, Meyer sound is having 3 analog controllers. It's called LD1, LD2, and LD3. And the low-pass filters for this controller is exactly the same filter as this. Only that in the analog controllers, you cannot change the frequency as many frequency range as you can have in the digital controller. Let me show you a high-pass filter in the digital Meyer sound controller. The Meyer sound controller Galileo is having 2 options of high-pass filter. One, it's called second order in the label. What we can learn here, that this filter, it is a 12 decibel per octave filter. 12 decibel per octave filter. But what we can see also, we can see here that before the cutoff frequency we have some increase. And the increase goes up and down. So this up and down shows that the filter is Chebyshev type 1 with a ripple that is around 1 dB. So you can see that the first option of the Galileo controller in the high pass filter is a Chebyshev type 1 with a ripple of 1 decibel, and it's second order. This filter also is implemented in the LD1, LD2, and LD3, but in these processors it is not possible to have so much flexibility in the frequency range. And let me show you one more. This last one, it is this one. Okay, it's been open. And this is the second option of a high pass in the Galileo controller. And then look at this. This shows in the stop band 1 and 2. So this is order number 2 of Chebyshev type 2. But also it shows a little bit of ripple of around half dB in the pass band. For this reason, this is called an elliptic filter. And in the processor Galileo, the name for this filter is called elliptic. What is the stop band attenuation? Let's count how many divisions of 3 decibels. This is 3, 6, 9, 12, 15, 18, 19, around 19.5 decibels of roll-off. And this same filter is implemented in the analog controllers LD1, LD2, and LD3 without the flexibility to change the frequency range so much as in the controller Galileo. So maybe if you are thinking why we want to use these very strange filters, the answer for this is the group delay. And for this reason, it's important that we go back to group delay. So let me go back to the original presentation. And this is filters part 1. And this is where we are. Okay, so let's enter into the group delay. And all the graphics that I have shown before shows in the vertical amplitude in decibels and frequency in hertz. This is what we typically call a frequency response. But now I will show in the bottom a new graphic that we have not discussed before. This one in the horizontal is showing frequency in hertz, but in the vertical is not showing frequency, is not showing decibel. In the vertical is showing time as in milliseconds, in a way that the position where I am showing the arrow is exactly 0 milliseconds. This position is half millisecond, this position is 1, 2, 3, 4, and 5. And I show with orange the range of 5 milliseconds, or 4, or 3, or 2, or 1. I also chose steps of 0.25 millisecond changes between 0 and 1 in order to have more detail. And you can see that in blue color, it's a graphic that shows that the upper portion is no delay, but the lower portion, it's been delayed around 0.2 seconds. So what happens is that the portion that is the passband is the portion that is showing delay. And the portion that is the stopband is the portion that is not showing delay. Because of this, since we have different amount of delay in different frequency range, this is called group delay. The other interesting thing is that if this is the cutoff frequency, the cutoff frequency is the division for higher than this is no group delay, lower than this it maintains the group delay. So what happens if I bring the cutoff frequency down? As soon as we bring the cutoff frequency down, the group delay will increase, but the bandwidth of the group delay will reduce. So let's see, right now from 2K we move into 1K, the low pass cutoff, and the delay right now is around 0.4 milliseconds. And the range of the delay reduce in bandwidth, and the range of no delay increase in bandwidth. If I bring this cutoff frequency into 500 Hz, the frequency range of the passband reduce. So this means that the group delay bandwidth will reduce, but the delay will increase. So you can see right now that the delay is around 0.8 milliseconds, but the frequency range with delay reduce, and the frequency range with no delay increase. And the area of the cutoff frequency is the area where you can see that delay goes from 0 to the maximum and then stabilize in the lower portion. So that thing, it is the group delay. Every time you play with a filter, the filter works in this way. But the group delay is not only affected by the frequency of the cutoff, but also by the slope. So pay attention, because right now I will change this cutoff from 500 into 250. What we can expect as soon as this is 250, the group delay we expect to increase. But because I will move the roll-off from order number 4 into order number 2, let's see what happens. So this is order number 4 in 500 Hz. So what I will do is go 250 order number 2. So this is 250 in order number 2. You can see that the group delay is not increasing. The group delay, it's similar, but right now the frequency range of the group delay reduce to this range, and the area with no group delay is the upper portion again. So then it's important that you realize the group delay depends in two parameters. Parameter number one, it is the frequency where you set the filter, and parameter number two, it is the slope or order of the filter. And what is more important is that if I play the opposite filter to this one, in this case a high pass, this one, the high pass shows that now the pass band is the area with no delay, and the stop band is the area with the delay. So it's very strange because it's exactly the opposite behavior. Before, the pass band is delay, but in the high pass filter, the pass band is the area with no delay. For this reason, it's important that you people understand that the group delay always is applied to the lowest frequency range, not to the highest frequency range. And what is more important is this: if we have a high pass and we have a low pass with identical cutoff frequency and with identical slope, the group delay will be identical. Let me play simultaneously a high pass and a low pass. Right now we have a high pass and a low pass, both at 250 Hz and both at second order. What we can learn here is that the low pass group delay is exactly the same as the high pass group delay. But here you don't see the pink one because the pink one is covered by the blue graphic. So we can see that the group delay with the high pass is identical to the group delay of the low pass. It's the same group delay. And this is what is very important for you to keep in mind when we perform the second session in July, because most of our decisions for what is called phase align depends in our understanding of the group delay. What happens if we try to understand this group delay but not with a graphic that shows milliseconds per frequency, but using a graphic that is called phase? Let's see what's going on with this. Oh, but before, I just remember what happens if I change the order of the filter. Let me show you. I have here 250 Hz high pass, and I am showing you first order, second order, third order, and fourth order. You can see that the first order produces less level of group delay in terms of milliseconds. The second order produces more group delay. The third order produces more group delay, and the fourth order produces the biggest group delay in this graphic. If I may have in this graphic order number 8 or order number 16, I will need to have more vertical range of time in order to show the group delay in the higher order filters. So this is something that you have to keep in mind. Higher the order means more group delay. Lower the order means less group delay. But also, shifting up the frequency, in other words, higher cutoff frequency means less group delay, but in a bigger range of frequencies. And lower the cutoff frequency means more group delay in more narrow bandwidth of frequencies. That is the way it works. So what happens if we enter into a new graphic? The new graphic is called phase. And I am pretty sure, because from the names that I can read here as participants, practically I know most of you, and I am pretty sure that you are familiar with what is the phase display. Anyway, just in case one of you is confused about what is a phase display, let me tell you. In the phase display, what we will have is not milliseconds, it's not decibels, but it's called degree. And the phase display will be, for any given frequency, 360 degree. So this means from the top to the bottom is 360 degree at any frequency. 360 degree, it is the same as one cycle, or the same as one time period, or the same as one wavelength. So if I am here in the position 0 degree, you can see that going in this direction, reach 180 in this direction, and reach the other 180 in the other direction. So the deviation from 180 to the opposite 180 is 360 degree. So in other words, the range in time in 1K is the time period of 1K, is one cycle of 1K, 1 millisecond. So this express 1 millisecond, this express 2 millisecond at 500 Hertz, this is 4 millisecond at 250, this is 0.5 millisecond in 2K, this is 0.25 millisecond in 4K. So here we have 4 different orders in this low pass, and this low pass is Butterworth with the cutoff at 1K and is order 1, 2, 3, 4. What we can learn here is that every order that we can see here produce more phase shift. Of course, the higher the order produce, more group delay. But the group delay display as phase goes in this manner. Order number 1 produce at the cutoff frequency 45 degree. Order number 2 produce 90. Order number 3 135, and order number 4 180. So it's very interesting because the sequence shows 45, 90, 135, 180. So we can very easily develop that every order multiplied by 45 is the total phase shift at the cutoff frequency. Order number 1 means 1 times 45. Order number 2, 2 times 45, that is 90. Order number 3, 3 times 45, 135. Order number 4, 4 times 45, that means 180 degree. With this idea, we can develop that if I show you order number 8, it's 8 times 45. So order number 8, it's 360 degree. So order number 8 at the cutoff frequency shows this. From 0, we reach one end, continue from the top, and go back to the center. So this center is not 0. This center now is 360 degree. 360 degree means that right now order number 8 produce one cycle of delay at 1K. One cycle of delay at 1K means one time period of 1K. This means 1 millisecond. If for some reason I take order number 8 and bring the frequency down to 100 Hertz, then the phase will have one full rotation in 100 Hertz. So this means that the delay, the group delay in 100 Hertz is 10 milliseconds. If for some reason I am using order number 16, 96 decibel per octave filter, this is 2 times the period of 50 Hertz. So period of 50 Hertz, it is 20 milliseconds. 2 times that is 40 milliseconds. So the group delay of a 96 dB filter in 50 Hertz will be 40 milliseconds. As you can see right now, the higher the order of the filter is better for filtering, better for isolation, but is worse in terms of phase shift or group delay. So how this group delay shows if we use another method of graphic that is called the impulse response. Let me explain for the very few of you that are not familiar with the impulse response. In the impulse response, the horizontal labels is time as in milliseconds, and right now this arrow is exactly in the position 0 milliseconds. To the right, the time increased to more milliseconds, and to the left, the time decreased. Then, in the vertical, we have amplitude, where 0 amplitude is exactly here. If we increase the amplitude, or if we increase the level, this goes up. But also, if we increase the level, it may go down. The difference between going up or down, it is polarity. If we increase the amplitude with positive polarity, this will go up. If we increase the amplitude with negative polarity, this will go down. So what we can learn here, having graphics of different orders of filters, is that the graphic shows that the peak moves to the right. So this means that we can locate more group delay. Higher the order, it's more group delay. And if we go back to the frequency response and the phase response, what happens if we compare Butterworth, Linkwitz-Riley, and the Bessel normalized at the same order and at the same frequency? In this case, the frequency is 1K, and we know that is 1K because Butterworth is at -3, Linkwitz-Riley is at -6, and the Bessel rectified is minus 7.5. So these three filters are at 1K. But I can see that these three filters shows 180 degree of phase shift at 1K. So this means that the three filters shows half of a millisecond at 1K. And this half of a millisecond at 1K is what we can see in the impulse response. So right now the peak of Butterworth, Linkwitz-Riley, and Bessel, it's exactly in the time of 0.5 milliseconds. And we can see that the Butterworth shows the peak a little bit taller compared to the Linkwitz-Riley, and the Bessel normalized is a little bit less amplitude compared to the other two. Why? This is because the level at the cutoff frequency. Butterworth shows more level, Bessel shows less level. Then in the impulse response, Butterworth shows more level, Bessel shows less level. But the center of the peak, it is 0.5 milliseconds. So, people, I have to tell you that this is the last slide of the presentation, and we are ready to